All right, we continue with day 69, the answers video. This is part 2. So we're going to move on to a weak acid reaction. There is a typo here we need to correct. Write a rice table for the weak acid, 1.2 molar oxalic acid. The Ka value says formic, and that was a change that I made. It didn't correct that. That's oxalic. Okay, you have to have the Ka value for the acid that you're using, not for some other acid. So we'll go ahead and make that correction, and their Ka value. Again, see how much of this you can do on your own. See if you can fill this out on your own, or if you can't, then identify what part you're getting stuck on. Okay? All right. Well, here's the thing. Oxalic acid, what's the formula for oxalic acid? I don't know. I actually do, but I'm going to say I don't know what it is. So what we're going to do is write it as a generic reaction. That's what you do. So I'm going to write this as HA, and then I'm going to add that to water. And then since it's not one of the strong acids, I know it has to be a weak acid, and so I'm going to use a double arrow here. It can go in both directions. Okay, what it's going to produce is this H is going to be passed to the water. It's going to form the hydronium. That's what all acids do. And then whatever the rest without that H, I'm just going to write it here as A minus. Okay, so again, that's how you do that. Don't get panicky because you don't recognize an acid. You probably won't in most of these problems. Okay, so go ahead and write in the initial. So it's 1.2 molar. We don't do anything with water. And we're going to assume since we weren't given... All right, let's keep going. So the change. Again, the coefficients, I'm not going to write them this time, but they're all ones. So this is going to be decreasing in concentration. And these coefficients are all 1, so it's just plus 1x. So now we come down here. And are you starting to see a pattern of how these rice tables kind of all start to look the same? And then you have an X and an X there. All right, so now we're going to write the law of mass action for this. And the general law for this equation is exponent is 1, but this time we're not going to write it because the coefficient there is 1. Okay, there you go. So that's the general form of the law of mass action. Now we're going to plug in values. We have Ka, we're given that right here. 10 to the minus 2 is a fairly big number. This is a fairly strong weak acid. What does that mean? It means that then we have x times x again. And if you feel like you get this, you can just call that x squared right away. And then this goes on the bottom, 1.2 minus x. All right, so here we go. We're going to make this assumption that we can cross that out. Otherwise, we're going to end up with a quadratic. So I'll let you go ahead and make it, but at the end do the 5% rule test and just make the statement, was it valid, to eliminate that. Okay, so now we're going to multiply both sides by 1.2. Okay, and that's going to give us 6.96. I'll go ahead and go with 6.96. We'll round it at the end. Okay. And that's going to equal x squared. These canceled. I should have crossed those out. Those canceled. All right, so now we get x equals. We take the square root of both sides. Do that. So we get x equals the square root. All right. And it's 6.96 times 10 hat negative 2. And that's going to give us 0.264. The value of x, so what does x represent? It is the value of the hydronium concentration. So let's go ahead and write that over here. And that's what we're asked. So that answers this question. I could also tell whatever this is, the rest of this, but we don't care about that. And it could also tell you what the concentration is here, but it didn't ask for that. So we're going to leave it at this. This is what it's asking for. Then down here it asks what's the pH of the solution. So it's simply and that gives us 0.58. That's pretty strong acid right there. But remember, we might have a lot of error by eliminating that X. So we're not going to go back and do it using the quadratic formula if we need to. Let's find out if we need to first. So the 5% rule. We're going to take the value of X, which is this. Concentration, which is 1.2, and multiply that by 100%. And that gives us a massive number of 22%. Means. Okay, it was not valid to eliminate X since the percent, 22%, is greater than 5%. So we should not have done that, and we should have used the quadratic equation to solve this problem. Okay? Other than that, though, we're going to move on. We know what we had to do, and we're just not going to do that part at this point. All right, let's keep going. Let's keep working through these. These should be second nature by the time you get back from the break. You need to be really good at these rice tables because we're going to use them a lot when we calculate buffers. Okay, now we're dealing with a weak base reaction. Ammonia, you saw that before as a base. It accepts a proton. All right, and what's put in tables in books is the Ka value of a substance. Then you would have to use this formula. Kw equals Ka times Kb, assuming 25 degrees. This would be 10 to the negative 14. And Ka would be what it is, and then you would figure out what Kb is using that form. So let's go ahead and write our reaction for NH3. Okay, it's a base. That's what bases do, is they produce hydroxide ions in water. So what's happening is a proton from water is being drawn over to the ammonia atom. It becomes, instead of NH3, NH4, but it's only the proton, not the electron, left the electron behind. So therefore it now has a positive charge. NH4 plus, it's called ammonium with an M at the end, ammonium. All right, and there's the hydroxide that it produced. So let's go ahead and fill in the rice table. Again, these start to all look the same after a while. As an X, let's write the law of mass action. It looks exactly the same as for an acid. Reaction, products. Okay, there we go. Now we can go ahead and plug in our variables as well as our Kb. Okay, that's what that'll look like. We're going to make our simplifying assumption. Remember in the last problem when the simplifying assumption wasn't valid, that was a -2. It was a pretty big number. Now it's a much smaller number. It's to the -5, okay? That's 1/100,000. So it's a much smaller number. And so the assumption, you can just look at the Ka or Kb and look at the exponent and get a sense whether that you can eliminate that X or not. But not absolutely. You just go ahead and do it and you'll find out at the end, okay? So this is all going to go away. That goes away. multiply by 2.6. These cancel. Multiply those two. Okay, we're going to take the square root of both sides, so this becomes x. Okay, and we go to our calculator and do that. Second, x squared brings up the square root. 4.68 times 10, caret negative 5, close parenthesis, and we get this. I'll go ahead and write it as a decimal number. And that's the value of x, okay? So what is that? It is the hydroxide concentration. That's what that represents. So we can put a molar behind that. So we can come over here for our answer, and I'm going to go ahead and figure out the hydronium concentration just for practice. So the formula is at 25 degrees. Solve that for H3O. Over what we just figured out it was, this number right here. Run that on the calculator here. Okay, and we get a very small number. This is a basic solution. You put a base in, so you're not going to have very much acid. That's what hydronium is. So it's times 10 to the negative 12th. Very small number. Down in the 1 trillionth range. 1 part in every 1 trillion. Okay? All right, so that's that. All right, what is the pH of the solution? All right. So we needed to figure that out anyway. That's why I did it, to get the pH. Or we could have figured out the pOH using that and then use that to figure out the pH. But I'll do it this way with the hydronium, so it's negative log of the hydronium concentration. Screen here. And it's 11.8. Remember, the higher numbers are basic, alkaline. So alkaline meaning base. So it's a very high number, meaning it's very little acid to it. It's a very basic solution. Finally, last thing we're going to do is do our 5% rule test. And this time I think we're going to pass. As I said, the reason is because the KB value was 10 to the minus 5. It's a very small number. That generally is reflective of what it means. Not very much of this reaction is taking place. It's staying pretty much as NH3 and not breaking off to NH4 plus. So it's this. The original concentration was 2.6. Trust me if you didn't see that up at the top, which you have in your rice table. Okay, so we're going to go ahead and do that. And we get less than 1%, 0.26%. Very small, way less than 5%. So it was valid to get rid of the x. Just write that out in a quick sentence so you know why you did that, okay? Is much less than, should put a percent sign there. So eliminating x was justified or valid, whatever word you want to use. Okay, and there we go. All right, let's keep going. What I'm really hoping is these problems are all starting to look the same in a sense that, okay, I see how they all are really kind of the same thing. Okay, another weak-base reaction. So here's a chance. See if you can do this one entirely on your own. So a concentration of 2.6 molar methylamine is placed in aqueous solution. By the way, an amine is a base like ammonia that has an NH, some sort of an NH compound within it. So NH3 would be an amine type of a base. Okay, it gives you a Kb. So go ahead and write the reaction. Again, you don't know what the formula for methylamine is. You're not expected to. So it just becomes this. We're just going to say it's a base. We're not going to say it's a conjugate base that has a minus sign. We're just going to call it B. And just add water. Okay, and what happens is H jumps over to here to become, doesn't matter, HB or BH, it doesn't matter how you write it. Okay, and we're going to say it's plus because it added a proton. And then when this water molecule got broken apart, part of it went to there and the other part is floating around. And it does what all bases do, it creates a hydroxide in the solution. Okay, so there you go, that's your generic base reaction. All right, let's go ahead and just plug things in. See if you can do this. I hope all of you can do this part by now. Okay, all the coefficients are 1. Okay, I just blitzed through that. Did you get that? Is there any part of it you don't understand? If you don't talk to me. Again, coefficients in front of these, you just assume that they're 1s. So there's 1s there. This side is adding because it was at 0. That's the only thing it can do is go up. So it's adding on the product side, decreasing on the reactant side. And then you subtract this, you add this, and there you go. Law of mass action. It's a base reaction, so it's Kb equals. Okay, so that's the general law of mass action for this reaction. Now we're going to plug in the values. 5.6 times 10 to the minus 4. X and X for those two right there. Okay, there we go. Again, we have a pretty low number there, okay? It's not a -2, it's a -4. Pretty safe assumption that it's going to be, you're going to be able to eliminate that. Again, -4 is 1/10,000. So that's a pretty small number, okay? Compared to this, which is in the 1s range, 2.6. That's between 1 and 10. That's a big number compared to that. Okay, so let's go ahead and eliminate this. Okay, get on screen here. Over 2.6, we eliminated that to get that. We're going to multiply both sides by 2.6. And multiply those two. Okay, and we get 14.56. Don't worry about adjusting the decimal in this scientific notation until the end of the problem. Right now we're in the middle of the problem. You can just go ahead and leave it like that. So I'm going to take the square root of both sides like that, and I'll just turn it around, put the x on this side. So square root of x squared is x, is that, and the square root of 14.56. Okay, and it gives us this. X, so that is the hydroxide value. That's what it's asking for here. That's the hydroxide value. So and I wrote that down incorrectly. I was trying to remind myself not to do that, and I did. There should have been a 0 in front of the 3. So it's 0.038, okay? It wants to know the pH of the solution. So we have to do 2 steps. We have a base here, a hydroxide. We want to get to the acid, the P for the acid, which is pH. So I can either convert this into H3O plus, and then from H3O plus to pH. Again, have your acid base roadmap. I'll do it here. So let's see the 2 ways we could do that, from OH to pH. So we go from OH, and what we can do is we can go from OH to hydronium H3O plus by using this right here. We know OH, we know 10 to the minus 14, so we can figure out the hydronium, the H plus. Once we have the H plus, then we can come over here and we take the H plus and we go negative log of H3O plus or H plus, and will give us the pH. So it's 2 steps. Either way you do it, it's 2 steps. Okay, so again, you go from here, you have this, you go to this formula right here and figure out what H3O plus is, and then you come up here, there's H plus or H3O plus, it's negative log of that, will give you the pH. The other way we could do it is this, go from OH to using this to POH. So once we know POH, we can come down here and we have POH, pH plus POH is 14, so if we know that, 14 minus that will give us that. I think I'm going to do it that way, okay? So I'm going to figure out the POH, and then I'm going to subtract POH from 14 to get pH, okay? You could have done it either way. All right, so let's do that. So we're going to go negative log of the hydroxide concentration, and that's this. Should write what that is. It's POH. So POH is, we're going to compute that. And you get 1.42. Okay, so we know that POH plus pH equals 14. So we're going to subtract POH from both sides. That should be POH. And we get 14 minus the POH, which is, which is this, equals, and that's going to be about 12 point, what is that going to be? 12.58. And that's the pH. So very high pH value means it's basic. Very high pH value means it's basic. So I don't know if you saw this. So it's 14 minus the POH, that, and it gives us that. That's the pH. So pH is 12.58. And that's very basic solution. Very high on the pH scale, up around 14 is going to be basic solution, not acidic at all. Okay, so there that is. Let's do our 5% rule. There's our value of X. And our initial concentration was 2.6 up there. And we get 1.46. I'll call it 1.5. Okay. So I'm just going to write elimination of x is okay. It was okay to do it, all right? Elimination of x, of that up there, what we did right there, is okay to do. All right. We're moving right along. We're chugging through these. Okay, we're up to another weak base reaction, but I gave you one where you're given the Ka. All right, so you're going to have to figure out what the Kb is. So for a base reaction, it's acetate ion, which is the conjugate base of acetic acid, and we're given the Ka of acetic acid, but that's not on the left side of this reaction. The acetate ion, its conjugate bases. So we're starting with that. So in other words, we're starting with this over here. Okay, and again, if you didn't remember what that formula is, you could have just written A minus. It's the conjugate base of a weak acid. So you could have written A minus. You could have written B as well, but since it is an ion, you could go ahead and do that. Okay, let's go ahead and finish the reaction, and then we'll figure out what the Kb is. So again, you're going to put this into H2O. It's a two-way reaction. You're going to end up with acetic acid over here on the right, and hydroxide, because that's what a base does. It creates hydroxides. All right, so let's go ahead and do this calculation here. So we have a formula that Kw at 25 degrees, that it states that it's going to be 10 to the minus 14, and that equals Ka times Kb. Okay, and we're given the Ka right here, so we're going to plug in the numbers. Okay, so you're going to divide both sides by this, and I'll just come down here and write it. Go ahead and do that calculation. And we get 5.6 times 10 to the minus 10. Okay, that's a very weak base. 10 to the minus 10th is a very weak base. It means in very few cases is a hydronium, a proton, going to jump from the water over to this. Very, very few times with that 10 to the minus 10. That's a very small number. So that reaction almost doesn't take place, in other words, is what it's saying. Okay, let's go ahead, though, and do the reaction. So it said we started with a 0.9 molar of the acetate. Everything else is the same as what we did before. Okay, there you go. Let me kind of block this off because that was just to figure out the Kb value we needed. So now we're going to write the law of mass action. Okay, now we're going to plug in our variables as well as our calculated Kb value that we came up with. So, and the initial concentration. I'm off screen, I see. Okay, so let me see what I did. I plugged the Kb value that we figured out right there. I put it in there. Again, this has been in every problem. It's x times x right there. And then over here it's 0.9 minus x right there. And you're absolutely guaranteed that you can get rid of this x. It's going to be a super tiny number if that's a 10 to the minus 10. So we're going to get rid of it. Go ahead and write this down here. Like that, so I don't keep going off screen. Okay, now we're going to go 0.9. Both sides multiply, cancel, and you have x squared equals 0.9 times 5, 6. and it's 5.04. Square root of both sides, and you get x equals and it's really tiny, so we're going to use scientific notation because it's so small. It's 2.24 times 10 to the negative fifth. Okay, very small x. I mean, super tiny compared to the original concentration, which was 0.9. That number right there, it's very small. Okay, so that is x. So what does that represent? That represents right there x, the hydronium concentration. That's what it asked for. That's all we're going to calculate here. Well, it asked us for pH, so we have to do that. So the concentration of hydronium at equilibrium is this number. And it is molar. It's a concentration. All right? Okay, so down here it asks for pH. So we're going to do it the other way. The last time, in the last problem, we converted OH concentration to POH and then said 14 minus POH equals pH. We're going to do it this time. We're going to do it with this. Very much the same way we calculated the KB. It looks very similar. Okay, so KW is 10 to the minus 14th. We just have the OH concentration there. And the hydronium ion concentration is what we're looking for. So we divide both sides by this. So I'm going to come down here and just do that. All right, and I'm off screen. All right, so there it is. So I just divided both sides by this, so it becomes 10 minus 14 over that. Is going to be the concentration we're looking for. No, well, it is, okay. It's not the final answer we're looking for, but that's it. Ten to the minus 14th divided by 2.24. Okay, and that gives us an H3O concentration of this. Okay, so now to get pH, we take negative log of that. And that gives us 9.35, which again is above 7, so that makes it a basic solution. So that's the pH, that's what we're looking for. All right, again, so what did we do that time? We had an OH concentration, so this time what we decided to do is we decided to take that concentration, come down here. We know that, we know the 10 to the minus 14, that gives us the hydronium H3O plus concentration. Once we have that, then we come up here to that spot, negative log of that gives us the pH. So it's a two-step process either way, but there's two different ways to get there. That's why you want to become familiar with this and how to maneuver around that. Okay, let's see how many more we can get in. I don't like the videos to go much more than a half an hour, and this is definitely beyond a half an hour. Okay, here's what we're going to do. We're going to do what's called a common ion. This takes two reactions. I'm going to have to show you two different problems, in other words, to show you how a common ion problem works. So I just want to be sure that's where we are. Yes. Okay, so I'm going to wrap this video. It's at about 45 minutes, and get that up for you. And I'll see you on part 3.